Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 5 for our MCAT General Chemistry playlist, and this chapter is titled Chemical Kinetics. In this chapter, we're going to cover a couple of objectives. The first objective is titled Chemical Kinetics. Here we're going to talk about reaction mechanisms. We're going to understand how molecular interactions and collisions lead to chemical reactions, and then we're going to learn about the various factors that influence how fast chemical reactions occur. The second objective is titled Reaction Rates. Here we're going to understand the concept of reaction rate and how it is measured. We're going to learn how to experimentally determine the relationship between the concentration of reactants and the rate of the reaction. And then finally, we're going to explore the different orders of reactions and their implications on the reaction rate. With that introduction, let's go ahead and get started. Now, chemical kinetics, this is the branch of chemistry that is concerned with understanding the rates of chemical reactions. It involves understanding the mechanisms by which reactions occur, the factors that influence these rates, the energy transferred during reactions, and how different variables contribute to the rate of a reaction. Now, to begin to understand this, we're going to discuss a concept that doesn't actually fall under the realm of chemical kinetics. Instead, it falls under the realm of thermodynamics, but it's going to be really important for us to understand nevertheless. This topic is Gibbs free energy, and while we will cover it in detail in Chapter 7 when we cover thermochemistry, I do want to define it early on here today. Gibbs free energy is a measure of the amount of energy available to do work in a chemical system. Gibbs free energy is a thermodynamic quantity that combines enthalpy and entropy to predict whether a reaction will occur under constant temperature and pressure. And it has the following equation. Delta G, the change in Gibbs energy, is equal to the change in enthalpy minus temperature multiplied by the change in entropy. Both of these are concepts we're going to discuss later. But the important thing from this reaction to understand is that reactions can be classified as spontaneous or non-spontaneous based on the change in Gibbs free energy. Therefore, the change in Gibbs free energy determines whether or not a reaction will occur by itself without outside assistance. Now, if delta G is negative, then the reaction is spontaneous. It will proceed without outside assistance. But if delta G is positive, then the reaction is non-spontaneous. Now, it's really important to pause now and note that even if a reaction is spontaneous, this does not necessarily mean that it will happen or occur quickly. In fact, nearly every biochemical reaction that enables life to exist, while perhaps spontaneous, proceeds so slowly that without the aid of enzymes and other catalysts, measurable reaction progress might not actually occur over the course of an average human lifetime. And so here, we've made a very, very important point. Just because a reaction is spontaneous or not, has no implications about how fast or slow the reaction is actually going to proceed with. All right, so in other words, saying that a reaction is spontaneous is not the same thing as saying that a reaction will proceed quickly. And this allows us now to explain the difference between thermodynamics and kinetics. Thermodynamics is concerned with the energy changes that occur during a chemical reaction, while kinetics is concerned with the rate at which a reaction occurs. So in other words, thermodynamics deals with whether a reaction will occur or not, while kinetics deals with how quickly that reaction will occur. And so while thermodynamics can tell us whether a reaction is energetically favorable, it cannot tell us anything about the rate at which the reaction will occur. So this is going to help us then transition to the main point of this chapter, which is kinetics. Kinetics is the study of the rates at which chemical reactions occur and the factors that affect these rates. To begin to understand kinetics, let's also talk about reaction mechanisms. And let's start with an example. Let's say that you have reactant A2 and reactant B, and you have 2 moles of reactant B. They react together, A2 plus 2B, to give you product AB, and you get 2 moles of this product. This balanced chemical equation, it provides a macroscopic view of the overall reaction, but it does not detail the step-by-step process by which these reactants actually transform into products. Balanced reactions, all right, and equations are useful for determining things like stoichiometry, limiting and excess reactants, theoretical yields, like we've discussed in the previous chapters. However, they rarely provide an accurate representation of the actual steps that are involved in the chemical process going from reactants to products. Many reactions actually proceed through multiple steps known as the reaction mechanism. And understanding that mechanism is really crucial for comprehending how and why reactions occur at particular rates. Now, a reaction mechanism describes the detailed process by which reactants convert to products through a series of intermediate steps. So again, considering this example we have written, this reaction suggests that 2 molecules of B collide with 1 molecule of A2 to form 2 molecules of product AB. However, it's more realistic to assume that this reaction actually proceeds through a couple of elementary steps rather than a single event. So for instance, the mechanism for that reaction might actually involve 2 steps, where step 1 has A2 plus 1 mole of B reacting together to form A2B, and then A2B plus another mole of molecule B react together to finally form our product, 2 molecules or moles of AB. You'll also notice that one step is labeled slow and the second step is labeled fast. So here, the first step is slower and thus determines the overall rate of the reaction. This slower step has a name. This is known as the rate determining step because it limits how fast the reaction can proceed. Now, something else you notice is there is this molecule A2B. This is an intermediate. Intermediates are species that are formed during the reaction, but they do not appear in the overall balanced equation. So they're produced in one step and then consumed in another, and their presence, while not listed in the reaction step, in the reaction equation, is still really important and crucial for understanding the reaction mechanism. So two important points to be made here is rate determining step. That's the slowest step in a reaction mechanism that controls the overall reaction rate. And intermediates. These are important. These are species that appear in the reaction mechanism, but not in the overall balanced equation. They still play a really important role in the stepwise progression of the reaction. Now, with that, when we describe chemical reactions, it's really essential to understand not only the macroscopic equation, but also the microscopic interactions that occur at the molecular level. So what we're going to do is, again, consider our reaction. A2 plus 2B give us 2AB. While the balanced chemical equation provides an overall picture, we need to know what the actual interactions between A2 and B are that produce AB. And there's various theories that explain these atomic level events. One crucial theory is the collision theory of chemical kinetics. For a reaction to occur, molecules must collide with each other. The collision theory states that the rate of a reaction is proportional to the number of collisions per second between the reacting molecules. However, not all collisions result in a chemical reaction. An effective collision, one that leads to the formation of products, has to satisfy 2 conditions. What are they? The first condition is correct orientation. The molecules must collide in a specific orientation that allows the proper atoms to interact and form new bonds. The second condition is sufficient energy. The colliding molecules must have enough kinetic energy to overcome the activation energy barrier, which is that minimum energy required for a reaction to occur. Now, the activation energy, this is crucial in determining whether a collision will be effective. Only a fraction of colliding particles have sufficient kinetic energy to exceed this energy barrier, meaning that only a fraction of all collisions are effective. This leads us to discussing how we express the reaction rate. The rate of a reaction can be expressed using this formula. Rate is equal to Z times F, where Z is the total number of collisions occurring per second, and F is the fraction of collisions that are effective. Now, a more quantitatively rigorous analysis of the collision theory is provided by the Arrhenius equation, which is this equation you see right here. K equals A. A here is the frequency factor, which indicates how often molecules collide in the correct orientation. Then we have this E, this is Euler's number, all right? This is an irrational number like pi. It is raised to a factor of minus EA, where EA is the activation energy of the reaction, divided by RT. R is the ideal gas constant, T is the temperature in Kelvin. Now, the Arrhenius equation shows that as the frequency factor A increases, the rate constant also increases. Similarly, as the temperature T increases, the exponential term, this whole exponential term right here, becomes less negative, leading to an increase in K as well. And so the main point here to take away, higher temperatures and lower activation energies increase the reaction rate. Okay, so in short, the factors influencing collision frequency are the frequency factor. The frequency factor can be increased by raising the number of molecules in a vessel. More molecules means more opportunities for collisions. The other factor influencing collision frequency is concentration and temperature. Higher concentrations and temperatures lead to more collisions and consequently higher reaction rates. Now, the next topic we want to cover that will further our understanding of the microscopic interactions that happen during chemical reactions is transition theory. All right, so this happens to understand the microscopic interactions that happen during chemical reactions. Transition theory allows us to kind of visualize this better. When molecules collide with energy equal to or greater than the activation energy, they form a temporary high energy configuration called the transition state. All right, transition state or activated complex. In this state, old bonds are partially broken and new bonds begin to form. The transition state then dissociates into products, fully forming the new bonds. So you can kind of visualize this here. What did we start off with in our reaction? It was A2. There's A2 plus 2 molecules of B. All right, here's our 2 molecules of B. And then they form 2AB products. And so in our transition theory, what's happening when molecules collide with energy that's equal to or greater than that activation energy, they form temporary high energy configurations like the one that you see right here. This is a transition state. There's the breaking of some bonds, the formation of new bonds, and this happens right before we form our final products. The transition state is represented at the peak of the energy barrier between reactants and products. And the energy required to form the transition state from the reactants is that activation energy. So far, we've talked about collision theory and we've talked about factors influencing collision frequency, like frequency factor, temperature, and concentration. Some of that is summarized here in this diagram. We've also talked about transition theory, and we discussed this high energy configuration called the transition state or activated complex. Now, to kind of elaborate on that transition state and to begin to visualize these concepts, chemists use free energy diagrams, also called reaction coordinate diagrams. They essentially plot the change in Gibbs free energy against the reaction progress from reactants to products. So here you see that the y-axis represents the change in Gibbs free energy, and the x-axis represents the reaction progress, aka time. Now here for this first diagram, what you notice is that the reactants have a higher energy than the products. Now, if you take the difference in energy between products and reactants, the delta G is going to be negative. Therefore, that means that this reaction is spontaneous. We discussed this earlier. A negative delta G means that the reaction is spontaneous. So if you were looking at this energy diagram and you note that the reactants have a higher energy than the products, then the delta G here is going to be negative and this reaction is spontaneous. This also means that energy is released. Now, to note also here, this highest point, this is the transition state. It represents the highest energy level, indicating the activation energy barrier. You also see that for this second diagram. Now, what you notice here is that's different is that the reactants actually have lower energy than the products, and so the delta G, the difference between the products and reactants, that delta G is going to be positive, and that means that this reaction is not spontaneous. Again, this highest point here, transition state, represents the highest energy level, indicating the activation energy barrier. Wonderful. Now, by understanding these principles, we can analyze and predict the behavior of chemical reactions more accurately. And we're going to be revisiting this again in Chapter 7. Now, having discussed the foundational aspects of collision theory and how molecular interactions and energy barriers play a crucial role in chemical reactions, it's important for us now to dive deeper into the kinetics of reactions to understand the factors that influence how fast reactions occur. This transition will help us link the microscopic interactions to the macroscopic observations of reaction rates. To begin, I want to introduce the rate of reactions. We're going to elaborate on this further in the second objective. But the rate of a chemical reaction, it refers to how quickly reactants are converted into products. And understanding reaction rates is vital for controlling and optimizing chemical processes in various applications, from industrial synthesis to biological systems. Now, a rate equation, also known as a rate law, quantitatively describes how the rate of a chemical reaction depends on the concentration of the reactants. And the general form of a rate equation is as follows. Rate is equal to K, where K is the rate constant. This is a proportionality factor that is specific to a particular reaction at a given temperature. Then that's multiplied by the concentration of the reactant A, raised to a reaction order, M, multiplied by the concentration of reactant B, also raised to some reaction order. So here, A and B are the concentration of the reactants, M and N are the reaction orders with respect to each reactant. These are determined experimentally. Now, the reaction order indicates how the rate is affected by the concentration of the reactant. More on this later, because what we want to discuss next is, well, what are the factors that influence reaction rates? Several factors can influence the rate constant K and consequently the overall reaction rate. These include activation energy, temperature, steric factors, reactant concentrations, and the presence of catalysts. So let's talk about each point one by one. Let's start with activation energy. So let's write this down, activation energy. The activation energy is the minimum amount of energy required for a chemical reaction to occur. Reactant molecules must collide with sufficient energy to overcome this barrier. The higher the activation energy, the slower the reaction rate, because fewer molecules are going to have enough energy to react. On the other hand, a lower activation energy results in a faster reaction rate because more molecules can surpass the energy barrier. The next point is temperature. The rate of most reactions increase with temperature. Temperature is a measure of the average kinetic energy of particles. As temperature rises, the kinetic energy of molecules increases, leading to more frequent and more energetic collisions. Now, this increases the proportion of reactants with enough energy to surpass the activation energy, thereby increasing the reaction rate. Now, it's often said that raising the temperature by about 10 degrees Celsius approximately doubles the reaction rate, although this is a generalization, okay? And it may not apply to all reactions. There's also the important note that extremely high temperatures, they can denature things like catalysts and enzymes, and that might significantly decrease the reaction rate. Then we also want to talk about steric considerations. All right, steric considerations are really important. So steric hindrance, this refers to the physical obstruction that's caused by bulky groups within molecules that prevent reactants from coming close enough to react effectively. Large substituents can block the reactive sites of molecules, making collisions less effective and slowing the reaction rate. Thus, reactions involving smaller, less hindered molecules generally proceed faster than those with really larger, more hindered reactants. Another important point is concentration, reactant concentration. The rate of a reaction is generally proportional to the concentration of reactants. Higher concentrations mean more molecules are available to collide, leading to an increased number of effective collisions per unit of time. This relationship holds true for all reactions except zero-order reactions. We're going to talk about that here shortly. Zero-order reactions, the rate is independent of the concentration of reactants. But for all other kinds of reactions, this relationship holds true. The last point that we want to talk about are catalysts. So catalysts are substances that increase the reaction rate without actually being consumed in the reaction. They work by lowering the activation energy, either by providing an alternative reaction pathway or by stabilizing the transition state. Now, catalysts, they may interact with reactants also to increase collision frequency, to potentially change the orientation of reactants, to make collisions more effective, to donate electron density, or to reduce intramolecular bonding. Enzymes, this is a type of biological catalyst, they play a crucial role in speeding up biochemical reactions. Now, with that, we've completed Objective 1, and we can move into Objective 2. In this section, we want to explore the concept of reaction rates in more detail. And to do that, we want to take a step back and really define the word rate. Rate is a change in some quantity over some unit of time. And specifically here, we're interested in the rate of reaction. The basic definition of the rate of reaction is the change in concentration of reactants or products over a given time period. And so that tells us how quickly a reaction proceeds by measuring how much of a reactant is consumed or how much of a product is formed in a specific time frame. So then for a general reaction like you see here, where we have A moles of reactant A plus B moles of reactant B, giving us C moles of product C and D moles of product D, we can write the following rate expression here. Now here what we see is these are the concentrations of reactants and these are the concentrations of the products. All right, we're writing the change in those concentrations and they're all divided over delta T. This is some change in time, some time interval. You notice that for the units, for the reactants, there's a negative sign. The negative sign indicates that the concentration of the reactants A and B decrease over time. And there's a positive value for the products because those are being formed over time. In addition, there's these coefficients in the denominator, lowercase a, b, c, d. These are to normalize the rate with respect to the stoichiometry of the reactions, and this ensures that the rate of disappearance of reactants and the rate of appearance of products are consistent with the balanced chemical equation, and that's why we can set the rate of these changes to equal each other. Now, to that point, for nearly all forward irreversible reactions, the rate of reaction is proportional to the concentration of the reactants, each raised to a power that reflects the reaction order with respect to the reactant. This is expressed in this equation right here. All right, we saw this earlier. Now, an important point to make here is that X and Y, we saw them earlier as N and M, whatever letters you want to use here, whatever order that the concentration of the reactants are raised to, these are called reaction orders. With respect to each reactant, they're determined experimentally. And this is important because reactions, they do not come with handy built-in speedometers, right? To determine the rate law for a reaction, we have to perform experiments where we measure the initial rate of reaction under varying concentration of reactants. And this equation captures that relationship. Now that we've introduced these concepts, I do want to pause and clarify the difference between the two expressions that we have written as rate equals something. All right. For this first one that we've written, this rate expression that demonstrates change in reactants and products over time, this is just a basic definition of the rate of reaction. It expresses the speed at which reactants are used up or products are formed. So for example, if you start with a certain amount of reactant A and then measure how much of it has been used over a specific period of time, you're calculating this type of rate. It just gives a direct measure of how fast the reaction is proceeding at any given moment in reference to either the reactants or products. Now, the second one that we introduced, this is our rate law. This is the rate law of the reaction. It provides more detailed information. So it's a mathematical model that describes how the rate of reaction depends on the concentration of the reactants. We also have this rate constant, K. All right, this is a proportionality factor that is specific to the reaction at a given temperature. We also noted X and Y. These are the orders of the reaction with respect to the reactants A and B respectively. These values, again, have to be determined experimentally. They indicate how changes in reactant concentrations affect the reaction rate. And so in short, the rate expression tells us how the appearance and disappearance rates of the products and reactants relate to one another. It's just a fundamental definition of reaction speed. And then the rate law over here tells us how the rate is related to the concentrations of reactants, incorporating the rate constant K, which is a proportionality constant, and or a constant of proportionality, and the reaction orders. Now, with all this new information, it's also important for us to discuss common pitfalls or traps and clear the air of that so we don't have any misconceptions. So let's begin that part now. The first common pitfall is assuming reaction orders are the same as stoichiometric coefficients. So one common misconception is the assumption that the reaction orders in the rate laws are the same as the stoichiometric coefficients. This is not correct. While stoichiometric coefficients indicate the relative amount of reactants and products involved in the reaction, reaction orders describe how the rate depends on the concentration of each reactant, and that actually has to be determined experimentally. All right, so for example, in a reaction that says 2A plus B gives us C, the rate law is equal to K, concentration of A, concentration of B, and then the stoichiometric coefficients do not determine the reaction order. We don't know what power to raise these to. We have to determine it experimentally. You cannot take this 2 and just place it right here, take this 1 and place it right here. These are not related. All right, the rate, reaction orders, these have to be determined experimentally. The second common trap that students fall into is mistaking the equilibrium constant expression for the rate law. Okay, so don't confuse the equilibrium constant expression with the rate law. The equilibrium constant K expression relates the concentration of reactants and products at equilibrium. So this is where we say that K is equal to the concentration of the products, if we're looking at this general form right here, over the concentration of the reactants. This is not the same K as this. Those are two different things. Do not confuse those. Each reaction also has a unique proportionality constant K. The third mistake, and actually I kind of just said it, is mistaking this K in our rate law as a constant that is the same number for all conditions. All right, that's a frequent mistake to assume that the rate constant K is the same under all conditions. K is actually specific to a particular reaction, and it can also vary with temperature and other conditions. So that's why we didn't assign this K a value like when we introduced Planck's constant. That was a real constant. It has a value that is the same all around. We gave you the number for that. K here, we don't have a number for it because it's different for every reaction and for every condition. Our last common mistake that we want to talk about is assuming equilibrium principles apply only at the end of the reaction. So many people incorrectly believe that the equilibrium principles are relevant just at the end of a reaction. In reality, equilibrium concepts describe the balance between the forward and the reverse reaction, and that's a dynamic process that occurs simultaneously. Equilibrium can be achieved at any point where the rates of the forward and reverse reactions are equal. And so even during the reaction, the system continuously adjusts to approach equilibrium, not just at the end. Now, keeping that in mind, all right, and before we dive into an example problem, I just want to reiterate some really important points here, all right, our takeaway message. The values of K, X, and Y in the rate law equation, those are all determined experimentally for a given reaction at a given temperature. The rate law is an empirical relationship that shows how the rate of a reaction depends on the concentration of reactants. When you're given experimental data on the MCAT, like we're going to see in this first practice problem we're going to do, you may be asked to determine the reaction order. Typically, the initial concentrations of the reactants and the initial rates of product formations are provided in a table, and the steps to determine the reaction order is as follows. First, you're going to identify a pair of experiments. You're going to look for a pair of experiments where the concentration of one reactant changes while the concentration of the other reactant remains constant. Then, when you've identified a pair of experiments like that, you're going to analyze the rate change. You're going to observe the change in the rate of product formation. Any change in the rate can be attributed to the change in concentration of the one reactant. Then you're going to determine the reaction order. Use the rate changes to determine the reaction order for each reactant, and this involves comparing the ratio of the rates and the ratio of the concentrations. And then finally, you can calculate the rate constant K. Once the reaction orders are known, you can use the rate law to solve for the rate constant K. All right, now that's a lot of information and that's a lot of steps to keep in mind. Let's put it into effect by tackling this practice problem together. For this example, we're told, given the data below, find the rate law for the following reaction at 300 Kelvin. We have A plus B gives us product C and D. Now, the first thing that we want to do is we want to compare trials to determine the order with respect to B. We are just going to start with that. All right, so what we're going to do is we're going to compare trials 1 and 2. All right, and that is because here in trials 1 and 2, the concentration of A is kept constant, but the concentration of B is being changed. And that's exactly what we were saying earlier. We're going to identify a pair of experiments where the concentration of one reactant changes while the concentration of the other reactant remains constant so that we can figure out the order with respect to one of the reactants. And we're going to actually do it for both reactants, but we're just starting with determining the order with respect to B. And so trials 1 and 2 are perfect because the concentration of A remains constant at 1 molar, while the concentration of B is doubled. All right, it's doubled. Now, the rate increases. These are the rates right here. I should have written the title. This is the rate for this concentrations. All right, rate initial in units of molars per second. So what we see here is that for the concentrations of reactant B, it doubles. The rate quadruples. All right, the rate increases from 2 to about 8.1, and that is about a quadruple increase, right? Going from 2 to 8 is about times 4. Now, this approximate factor of 4 suggests that when the concentration of B is doubled, the rate increases by a factor of 4. This indicates a second order dependence on B because you have concentration of B in the second trial over the concentration of B in that first trial raised to some factor is going to be equal to 2 to some factor equal to 4. All right? This approximate factor of 4 suggests that when the concentration of B is doubled, the rate increases by a factor of 4, and that indicates a second order dependence on B. So y is equal to 2. So when we write our rate equation, our concentration of B is going to be raised to a factor of 2 to indicate that there is a second order dependence. Now we could do the same thing for A. So I'm going to erase this. We just figured out the order with respect to B. Let's do it with respect to A. In order to do that, we're actually going to compare trials 2 and 3 because in trials 2 and 3, our concentration of B is the same, but our concentration of A changes. It doubles. Now, when it doubles, what happens to the rate? The rate also doubles. Okay, so this is interesting. The rate increases from 8.1 to 15.9. So this is approximately going from 8 to 16. That's twice as much. All right, so we calculate the ratio to be times 2. Now, this approximate factor of 2 suggests that when the concentration of A is doubled, the rate doubles. This indicates a first order dependence on A, so we can set it up similarly, right? If we're writing a ratio of the concentration of A in trial 3 and the concentration of A in trial 2, and we're trying to figure out what that reaction order is, well, we note that when the reaction concentration doubles, going from trial 2 to trial 3, our rate also doubles. And that means X here is equal to 1. That is the reaction order for A. So when we write A, we raise it to power of 1 because there's a first order dependence on A. Okay, this is good. This is getting us somewhere. Now we can kind of write the rate law for ourselves. So this is going to be equal to rate is equal to K multiplied by the concentration of A raised to the first power multiplied by the concentration of B raised to the second power. Now, the last thing that we have to do is actually figure out the value of K. How do we do this? Well, we can use any set of data to solve for K. So for example, we can use trial 1. We can plug in values to figure out K. How do we do this? Everything is given to us. If we're taking trial 1, we can take any trial, by the way. I'm just choosing trial 1. We can put in the concentration for A here, this 1 molar. We can put in the concentration for B from trial 1, also 1 molar. And then we can put in the rate, 2 molar per second. And then we can isolate K to solve for it. So we're going to put in the values that we know equals to K multiplied by 1 to the 1 power and 1 to the second power. This gives us 2 molar per second is equal to K multiplied by 1 squared, which is just 1, multiplied by 1 to the 1 power is just 1. So we just have 1 over here on this side. All right, and we could get rid of the units here just to make this calculation easier. We just have 2 equals K multiplied by 1. We can isolate K by dividing both sides by 1. K equals 2, and the units here is going to be molar minus 2 multiplied by seconds inverse. And there we have it. We figured it out. We figured out the rate law for the following reaction. Now with that, we can move into discussing reaction orders. We classify chemical reactions as 0 order, first order, second order, higher order, or mixed order on the basis of kinetics. So we're going to continue to consider our generic reaction of A moles of reactant A plus B moles of reactant B give us C moles of product C and D moles of product D for this discussion. So let's talk about it, starting off with 0 order reactions. A 0 order reaction is one in which the rate of formation of the product is independent of the concentration of the reactants. So this means that changes in the concentration of A and B, they do not affect the reaction rate. The rate law for a 0 order reaction is equal to concentration of A raised to the 0 power, concentration of B raised to the 0 power. And you know, anything raised to the 0 power is just 1. And here, K is going to have units of molar per second. And in this case, the rate constant K is the only factor that determines the rate of the reaction. Now, we can also talk about temperature and catalyst in reference to 0 order reactions. The rate constant K is dependent on temperature. Therefore, the rate of a 0 order reaction, it can be changed by altering the temperature. Additionally, adding a catalyst can also lower the activation energy, and that would increase the value of K. Now, graphically, we can plot the concentration of the reactant A versus time for a 0 order reaction. It's going to result in a linear graph, and the slope of this line is going to be equal to minus K. All right, the slope of this line is equal to minus K, indicating a constant rate of reaction. So that's our 0 order reaction. What about first order reaction? This is one where the rate is directly proportional to the concentration of a single reactant. So if the concentration of the reactant is doubled, then the reaction rate also doubles. If the concentration of the reactant is tripled, the reaction rate also triples. The rate law for a first order reaction can be written for our generic equation, A moles of A plus B moles of B give us C moles of product C and D moles of product D. It can be equal to K multiplied by the concentration of reactant A to the first power, or maybe it's dependent on reactant B, so we can also write a first order reaction rate for this generic chemical equation as rate equals to K multiplied by the concentration of reactant B to the first power. So either or, depending on which reactant our first order reaction actually depends on. Can go either way. All right, now here K has units of seconds inverse seconds. The graphical representation here, well, we can plot the concentration of reactant A versus time for a first order reaction. That's actually going to result in a nonlinear graph. So it's going to look something like this instead. But if we plot it for the natural log of the concentration, like you see here, versus time, that actually yields a straight line. And the slope of this line is minus K, indicating that the rate of reaction depends on the concentration of the reactant. Okay, so that's 0 order and first order. What about second order? A second order reaction has a rate that is proportional to either the concentration of 2 reactants or the square of the concentration of a single reactant. So again, based off of our generic chemical equation here, if we were trying to write the rate law for a second order reaction for this particular chemical reaction, it can be one of 3 things. The rate can be equal to K multiplied by the concentration of A to the first power and concentration of B to the first power. This is a second order reaction because the sum of the coefficients here, N and M, or X and Y, right, the reaction orders, sums up to 2. Or the rate can be equal to K multiplied by the concentration of A to the second power. That would be a second order reaction. Or the rate can be equal to K multiplied by the concentration of reactant B to the second power. Because we have two reactants, a second order reaction might just depend on one raised to the second power, or it can depend on both where each are raised to just the power of 1. And we can sum up the reaction orders to equal to, that would still be a second order reaction. Now K here has a units of inverse molar, inverse seconds. A second order rate law. This often suggests that a physical collision between two reactant molecules is necessary for the reaction to occur, especially if the rate law is first order with respect to each reactant. Now, as for graphical representation, we can plot the concentration of the reactant A versus time. For a second order reaction, this is going to result also in a non-linear graph. However, if we were to plot instead the inverse of the concentration, so 1 over concentration versus time, that's going to yield a straight line. The slope of this line is equal to K, indicating that the rate of reaction is dependent on the concentration of the reactant. Now, two additional things that we want to mention here briefly because they can get complicated and we don't really need to know a lot of complicated information about higher order reactions and mixed order reactions, but just some things conceptually. Higher order reactions, these refer to reactions where the sum of the exponents in the rate law is greater than 2. All right, so that would constitute a higher order reaction. These reactions are less common because they involve the simultaneous collision of 3 or more molecules, which is statistically less likely. In addition, the units of the rate constant K for higher order reactions will vary depending on the overall reaction order, but they also typically include higher powers of concentration and time to balance the rate equation. You can also have mixed order reactions. These are ones that do not follow simple integer orders with respect to reactants throughout the reaction. These can occur due to several reasons like complex mechanisms, intermediate formation, or varying reaction orders under different concentration ranges. Again, these topics are not considered high yield on the MCAT. For the purpose of this exam, it's just sufficient to have a basic understanding of the definitions without delving into too many extensive details. We'll also jump into a problem set right after to really help us understand all of these topics and put them into effect. Other than that, we finished our lecture. I hope that this was helpful. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.